Okay. As always, our recordings of our virtual meetups will be available on YouTube about a week after the meetup, and we'll post a message on YouTube when the recording is ready. Next, I am very pleased to introduce our speaker today, Hemanshu Kaul. Hemanshu Kaul is an associate professor in the Department of Applied Mathematics at Illinois Institute of Technology. He is a member of the Discrete Applied Math Group. His interests lie, broadly speaking, in discrete mathematics and operations research, especially graph theory, discrete and network optimization, and related mathematical and statistical models and algorithms, and interdisciplinary applications in transportation networks, computer science, and ECE, power networks and optimization. He is also interested in the ethical aspects of mathematical and optimization models, and particularly in equitable allocation of resources. So I'm very happy to pass it over to you, Himanshu.
Thank you very much. Thank you for the introduction, and thank you for the invitation, particularly to Dr. Choi. I think this talk will be, when I discussed this with Socheng with Dr. Choi earlier, I think this would be an unusual talk because I'm not going to talk so much about the computational aspects of the research that we did, but more from a more ethical or more philosophical perspective of how we apply or how we create mathematical models which are used in all sorts of applications these days, whether you use them, you apply them with help of computer programs or machine learning or anything like any of the new hot buzzwords in the computational world. But I want to step back a little bit and talk a little bit about a fundamental ethical perspective towards doing something like this. So thank you for being here. Let me share my screen. And feel free to stop me or interrupt me anytime you have any questions. I love discussing this stuff. It'll be a very high level talk. We won't really get into too many details, but if you have any questions, anything you want clarified, please don't hesitate to. I won't be able to keep track of the chat, but our organizer has very kindly, will kindly help me and tell me if there are any questions in the chat. Otherwise, you can unmute yourself and speak as well. We have a small enough group. I think that'll be fine. Okay, so I'm going to start with this. I'm going to talk a little bit about ethics in mathematical modeling, and then give you an example about applying those ideas in the context of public transit network design. So this includes work with my former PhD student, Adam Rumpf, who's at Florida Polytechnic now. So mathematical models, so mathematical models are ubiquitous in sciences, engineering, social sciences, and so on, because they serve as a conceptual representation of some observed phenomena that we are trying to understand. So some common examples of mathematical models are some of you who took Newtonian physics in high school or something like that, classical mechanics. You throw a ball, what is the trajectory of that ball? How does it travel? And so on and so forth. Motion of planets, population growth, epidemiology, which is very relevant these days, spread of diseases. How do diseases spread in a population? Microeconomic models, financial market, financial models. How do you create derivatives? How you put financial portfolios together? What is risk management, things like that. All of those and many, many more. All of these models are, in all these applications, are mathematical descriptions of some observed phenomena. You create that mathematical model, and then you work with that model to sort of understand the phenomena that you're trying to study. So, this is strange, not showing slide for some reason. Okay, doesn't matter. So, here's a simplified version of how the mathematical modeling process works. Right? So you're trying to understand a real world behavior. You cannot understand and study each and every detail of that. So you pick, based on the kind of question you're trying to answer, you pick certain aspects of it, make some simplifying assumptions about that, and then you write that description in a mathematical language of some sort. Right? You might be using variables. It might be an optimization model. It might be an economic model. It might be some other network model, things like that. It could be any of those things. It could be in terms of differential equations. So you write a mathematical description, and then you analyze or solve that mathematical description. You come up with some mathematical conclusions of some sort. I mean, when I say analyze or solve, it could be an algorithm. It could be a program that you wrote, which works with that particular model, analyzes certain data that you already have, and you come up with some mathematical conclusions based on that. Right? Because it's basically studying this mathematical description. So then what you do is you interpret what those mathematical solutions or conclusions mean in the context of the problem that you're trying to understand. That can be interpreted as an explanation of the phenomena or prediction, depending on kind of model you have. And then you check with the real life observations that you have, what you are explaining or predicting actually matches with what's happening in the real world phenomena that you're trying to understand. And so there's a very simple top level view of how this process works. Of course, it's not as simple as this loop like this. In fact, as you set up a model, as you analyze it, you might actually go back and you might feed back into this step and redo that step. As you go this way, as you look at the interpretation, you might realize, oh, maybe I need to solve it in a different way, or I need to get a different class of solutions and go back over here. Or you might go back over here and make some other assumptions over here. Or as you go along and you do the value, you realize that, oh, the explanation or prediction does not match with the real world behavior. So I need to go back and look at what assumptions I made. So in terms of math world versus real world, and I'm speaking of math as a very, very broadly, it is, math or computational world versus what's really happening in the real world. So there is this partition over here as you move from the real world into the mathematical world and then back into the real world. Okay, so this is just a simple description of what we try to do when we use mathematics in the real world. Of course, it goes without saying, and this is a very famous saying, that all models are wrong, but some are useful, right? Wrong in the sense that no model can have all possible situations included in itself. I mean, you always have to make certain assumptions, and based on those assumptions, you build a model and try to do something with that. But the reason we build models is because we are trying to understand some very complicated behavior, or we are trying to experiment with a very complicated, or we are trying to predict what's going to happen in the future based on some complicated phenomena. So the reason these models are, any such situation is useful, any such description is useful, is because it might reveal relationships which are not apparent superficially. You might be able to build strategies which are more sophisticated or powerful than a naive approach. And it allows for experimentation and simulation when it's impossible or too expensive to do in the real. I mean, these days, this is one of the big reasons in computer science kind of applications or computational applications, because you want to build a simulation model or experimental model where you can do things which would be too expensive to do in the real. So the question is now, I want to focus on this word wrong. I mean, as I said, wrong, it's talking about a one particular thing, right? Wrong in the sense that you have to make certain assumptions in your model. You have to go back. When you go through this very first step, right? As you go through this very first step over here, right? Oh, it's annoying. Give me a second. Something is strange. Right. Okay. As you go through this step, you are making certain assumptions which technically makes your model wrong. But the power of the mathematical modeling or power of doing these things is by picking the right kind of assumptions you make. This is also the source of the power of this particular modeling process. So the art of modeling, I always, when I talk to students about doing this or other collaborators, it's not, I mean, there is no scientific method by which you can do step 1, step 2, step 3, even though a lot of practitioners may try to make you believe that there is this step 1, you put in all this data into this black box and you get an output. Actually, to actually have a model and something that you can make sense of what's really going on, the art of making that modeling is not a precise step-by-step process. There is an art because you have to make the right kind of choices in your setup. And the choices you make act as axioms for your model. And they drive the whole modeling process from solution to interpretation and things like that. So if you look at a couple of examples like the classical mechanics, when you're talking about throwing a ball and understanding its trajectory or trying to understand the motion of planets, there is an implicit assumption that mass is fixed. It acts like a point. So it's a point mass. Forces act instantaneously. This worried Newton as well as all the way to Einstein, that how can forces act instantaneously? But that is an assumption we are making, that it acts instantaneously. And then you have things like Newton's law of motion. And then if you go on later to 20th century, we understand actually these implicit assumptions are actually even more relevant in the sense of when you talk about relativity or relativistic mechanics, you are talking about an assumption which says we are working with an inertial frame of reference, non-relativity, non-quantum kind of a setup. Because when you drop some of these assumptions, you get into more modern 20th century quantum mechanics or relativity theory, things like that. But the point is, based on the basic assumptions that we make, that is really the driving force of what allows us to do something meaningful or powerful with an example like this. Same thing with population growth. The fundamental, I mean, one of the earliest models for population growth was built in the late 18th century by Malthus, the Malthusian model, which was the first time a scientist tried to understand how are the resources on Earth going to keep track with the population growth. And he built a population model based on this assumption that change in population is proportional to current population, right? Because current population includes a certain population which is it can reproduce, and they give birth to a certain proportion, certain number of children. So fertility rate or something like that. So the change in population that happens is proportional to the current population. But if you just take that model, the Malthusian model, it gives you exponential growth in population. While Malthus was able to estimate that this growth in resources or food production will only be geometric rate. So his prediction was that human beings are in trouble because our food growth will not keep pace with the population growth, which is going to be exponential. But this is not completely accurate. I mean, this is true to a certain extent. This had to be modified to make more sense of it, that there is an environment limit to the population. As you reach the environmental limit, the population growth slows down and gives you a population growth which is not exponential, but what we call logistic growth. Right? So the point even if you don't know what the phrases I mentioned or technical phrases, even if you don't know what those things are, I'm just trying to make the point that as you make these assumptions, they help drive the model forward and give power to the assumptions that you're working with. So now we come to the first part of the talk, right? So if this model, this process makes sense, whether you go this way, and things like that, and we do these steps to understand some phenomena, the question is, where are ethical concerns important in this process as we go through? So if you look at this very first step, right? So when you're working with if it's a pure mathematical formula, which is very rare in real life, okay, maybe then you don't have that many concerns. But in reality, what you end up doing is you're using some numerical or computational technique based, maybe if you're using machine learning kind of a thing, then you actually are looking at some data from the real world, using part of that data to build an algorithm, a machine learning algorithm or something like that, to come up with certain conclusions about what's really going on in this particular model. So there, you must have heard of algorithmic bias, which has been a buzzword, a hot word for the last 5-10 years, that when you use these kind of machine learning techniques or other algorithms, there is a danger of introducing some sort of bias. So this is where ethical concerns come into this particular step of the process. You can think about what happens in terms of the algorithms you're using, are they biased in some particular way? In the second step, in this particular step, when you're interpreting math into the real world, here's an example of that, bioethics. When you're working with models for example, drug delivery systems, or you're working with models which talk about how medicine, a particular drug, is absorbed in the body, or how it stays in a particular body, what kind of useful and harmful. I mean, no medicine is completely just beneficial. There are always side effects, right? So when you build a mathematical model to see how those side effects affect you, you have to interpret the conclusions because they are going to apply to real people, to patients, right? So in that interpretation and application, bioethics is an important thing. This has been studied for ages, ever since we have modern medicine or pharmaceutical companies. Bioethics is an important part of the process because you're trying to use some idealized mathematical model and its interpretations, and then trying to say something about whether or not to apply those to real people. So bioethics is an important part of that. So that corresponds to, that's an example of something. So this step, verification, I mean, a lot of you must work with statistical models and things like that. Here's where data becomes important, right? If there is bias in your data that you're trying to build, that you're trying to validate this against, then that data bias or statistical bias might cause you to have erroneous conclusions about whether a particular model is good or not. This is where data bias creeps in here as well, because nowadays we use algorithmic methods which depend on a portion of the data that you have to train your algorithms for doing something like this. So algorithmic bias, bioethics, statistical ethics or data bias, all of these things are sort of things which people recognize and have been working on or thinking about for a long, long time. So my point is, even before you do all that, here is the very first step, which is often ignored, because oftentimes people work with, oh, this is the standard way in which we reduce this behavior to this particular model. This is the standard model, or this is the standard way in which we do things. So often this step is standardized. Maybe you can think of examples in your own career or in your own profession, that when you look at certain standard real world behavior, you have a description of that in your own technical language, which basically says, oh, this is the standard way in which we interpret. So when things get standardized, there is always danger of making the assumption that this is the way to do it, and there is nothing wrong with it. So you make that implicit assumption that this is unbiased, or you just ignore the possibility of ethical concerns. So this is the point I'm trying to make. So this is something that does not get enough byplay in our, in media, in otherwise, or within our community, within the scientific or computational community, is that when we should not be ignoring this step, and we should be thinking about, okay, if I'm just using standardized way of doing things, whoever told you, your leaders in your field told you this is the standard way of doing things, we should be questioning where those standards come from. Are they unbiased? So if that very first step is creating some sort of an inbuilt bias, then it's possible that we cannot overcome that bias even if you do everything else perfectly. Even if we avoid any bias in our computations, even if we avoid any bias in our statistical or data collection analysis, even if we avoid any bias in our real world recommendations. If there is an implicit bias in how we are doing this, it is going to affect everything else. And it's important for us to step back and understand what those choices are. Implicit, most of the time, those are implicit choices that we have made. Are those choices ethical? That's really the point of what I'm trying to say, sort of bring that to the forefront. So I pause for a moment and see if anybody has any question or comments till this point. Okay. Can't see faces, so I'm just, okay. Okay, I'm still here. Okay, good. Everybody's still here. Okay. Okay, so then let me, if there are no questions, then I'll continue. So, I mean, there could be a whole talk about what does ethics exactly mean and what do I mean by ethical standards. So I'm going to reduce several thousand years of mathematical thinking, of human thinking or philosophical thinking to a single slide, right? So that's, welcome to a short talk, right? So here are some perspectives on ethical standards. Utilitarian, will my choice create the most good and cause least harm? Rights, which choice best respects the rights of those who have a stake? I'm going to talk about a couple of examples which are sort of in terms of utilitarian or fairness and justice perspective. I'll have a couple of advertisements. If you want to learn more about real world examples of ethical decision making and real world case studies, Markula Center for Applied Ethics, is a great place to do that. If you do a Google search for this, you'll find a huge variety of real world case studies which talk about when ethical decision making is important. So that I don't have time to talk too much about that. Okay, so what I'm going to do is, now my real talk is starting. I'm going to give you a quick overview. We don't have so much time. I'm going to give you a quick overviews of two examples of trying to illustrate this kind of thing. So the first example will be a historical example to illustrate how this bias can create issues with what we are trying to do, even especially when we are trying to help people or when we are trying to understand how certain situations affect people. And second will be a personal example of my attempt to make sense of a standardized model, a standardized way of designing transportation systems, and trying to ask the question, can we rethink what assumptions we are making in that model and apply it to a situation where these ethical concerns are important? The question of equity, equitable distribution of resources is important. So I'll give you two quick overviews of these two examples. So I won't go through the whole timeline, but this is the first example. This is the historical example called the Love Canal controversy. I don't know, has anyone heard of the Love Canal controversy? This was a big hot thing in 1970s and 80s, maybe before most of you were born, maybe, I don't know. So this was a big thing because this was one of the early indicators of controversy about environmental concerns in our day-to-day life in the United States, particularly. So Love Canal was a small suburban town in New York State, close to Niagara Falls. And it was named for W.T. Love, who built a canal over there for a hydroelectric plant, which was never built. There is an electrochemicals factory was established in 1905. In 1942, 1952, this company was allowed to dispose several thousand tons of chemical waste in the canal in fiber and metal bags. They had nowhere else to put this waste, so they put it there. By 1953, the canal was full, so it was covered by soil and grass grew. 1956, in the boomer generation, as in the post-World War II generation, as the number of children grew really, really fast, the population was growing, a lot of young children. So there was demand for new schools. So a new school was built in the suburb of Niagara Falls City, in the city near there, near Buffalo. And soon a bedroom community grew around that. Now let's move to 1970s. Chemical odors became noticeable in the city. Soon there were newspaper articles and there were investigation, and the New York Department of Health found that there are lots of chemicals, including carcinogens, in the city. Not surprisingly, right, for us, right, from this perspective. So then they had to come up with, okay, what should we do? So it's dangerous to live there. So the New York Department of Health came up with the proposal that they will buy the houses which are closest to that particular site and relocate those residents. So, and they concluded, based on their study, which I'll soon talk about, they concluded that rest of the Love Canal far from the waste site is safe to live. So nothing for those people. I mean, they need to continue living. So in the same, as this was happening, Louise Gibb, who was a homemaker, she organized a residents association, and she sat down with a map of Love Canal, of the town, and put a pin on every home with a registered health problem. And soon she noticed, as she put on these, so this was the center part, and this is where the waste site was, right? And as she put these pins of where the houses with health problems were, she noticed some sort of a strange pattern. It didn't look completely random. It looked like some sort of a pattern. And then what she noticed was this pattern actually corresponded to, when she talked to older people and she looked at the old maps of the city, these patterns, these marks sort of corresponded to certain seasonal streams streams which get water only in certain seasons, and swales. So these would be the swales, because remember, they were connected to the Love Canal itself, and that's where the waste site was. So let's call these things wet homes, the homes which correspond to, which were on these parts of old streams and swales. So when they did a thorough survey of all the residents with help of Beverly Pagan, a cancer researcher from nearby research institute, they found that residents in wet homes were 3 times more likely to have different kinds of health problems than those in the dry homes, the homes which are not over. Okay, so they argued that, based on this, they argued that evacuation should prioritize residents from wet homes, and ultimately all residents should be evacuated because of this widespread pattern of contamination through the swales. But NYDH, New York Department of Health, disputed this, and they said they would only evacuate houses close to the waste site. With enough media coverage and all kinds of controversies, finally they prevailed, and much of Love Canal was vacated. And this was one of the major impetus to, you must have heard of Superfund sites. All major cities, all areas of US have certain Superfund sites, which are sites created to handle sites of major environmental disasters. And in 1980s, because of a way to handle this situation in Love Canal, the federal government created funding for these Environmental Protection Agency Superfund sites. Anyway, so it has a important historical importance for all of us who live here in the United States. So, okay, what's the point? So that was a story. So the point I'm trying to make here is, okay, what's really going on, right? There was this dispute between Pagan and the New York Department of Health scientists, because they were basically working with different mathematical models. In case of NYDH scientists, they built a mathematical model based on the assumption that toxins spread more or less homogeneously outward from the waste site. Right? So if this is my waste site, it all sort of spreads homogeneously like this. And as you get farther and farther away from the main waste site, the effect of the contamination becomes less and less. Okay. And this is traditional scientific practice, right? You start with this kind of a basic assumption, you build a model on that, and then you add complexity to these two. But the fundamental assumption doesn't change. That the fundamental assumption is that as you go farther from the waste site, the effect of the waste will become less. In case of Pagan, her analysis, her model was based on the fact that toxins spread faster through the paths created by seasonal streams and swales. So that created a completely different model. Then the question is, okay, what do you do? I mean, so you have two very different approaches to the same problem. Then the question is, what is the burden of proof? In case of the NYDH scientists, they said we need strong evidence that Love Canal is unsafe, because we have this standardized model which works in most situations. This is the correct way to do things. So if you want to claim that it's unsafe, you need to give us strong evidence that it's not unsafe. In case of Pagan, her point was that strong evidence is needed to conclude Love Canal is safe, since a mistake could result in damage to human life in the context of the history and available data. Because you're not looking at the data, you're making the assumption of homogeneous spread while it is heterogeneous spread. And then when you do the statistical modeling, and when you do the validation statistically, it will create wrong conclusions, because your fundamental model is based on homogeneous spread rather than heterogeneous, which is really what seems to be happening. And more importantly, in the context of the history of the situation, there is reason to believe that there could be damage to human life in this particular case. So this is an example of, so this is one of the things I want to advertise, is that this is an example of what is called the precautionary principle. So this originated in 1970s or even earlier historically. And in the Rio Declaration of 1992, representatives of 178 nations agreed on the statement that when there are threats of serious or irreversible damage, lack of full scientific certainty shall not be used as a reason for postponing cost-effective measures to prevent environmental degradation. So you can see this is a very of course, it's very vaguely written because all of these things are open to interpretation. But this is sort of like a principle about when there is a threat of environmental degradation, we should be looking in terms of damage to human life, right? So when you're making some decisions, when you are creating an algorithm, when you're creating a computational technique, when you're working with a mathematical model, and it's not just an abstract model in an abstract space, your conclusions or what your algorithm does has an impact on people, how they live their life, what happens to them, what they use. Maybe it's just a algorithm you wrote for cleaning up photographs, but the data you used or the assumptions you used were that, it's basically just people whose skin color looks like a particular color, while people who have a different skin color are not even considered in that particular algorithm or in the particular data that you're training that algorithm on. Then that will create an issue. That's an issue of a bias, right? So it has an effect on people. It has an effect on people who are working. And I'm not just using this example hypothetically. This is something that actually happened with certain software that Samsung, for example, created, and I think some other companies also, which had this kind of an issue, right? So that might, so when you have situations where your model and and what you're doing with it, whether computationally or mathematically or statistically, we need to take it as serious situation when it has an effect on actual people. Right? So I'll end this first part of the talk of this example with sort of saying, okay, some guidelines we could say are that when you're doing applications, when you're working with real life, the practitioners are not outside the system, right? Scientific objectivity is tricky. So just to use the example of the NYDH scientists, there is no, I mean, let me just clarify in my talk that I'm not claiming that they had they were, doing something bad or something not fair, because from their perspective, what they were doing was perfectly standard scientific practice. And they were not doing something that, that was wrong in any sense of the word, that was in the sense that things were done at that particular. But the thing was, not questioning the standardized model and just using it blindly doesn't mean that it is true or it is useful or it's meaningful in all particular situations. So when we have certain uncertainty of assumption and uncertainty of evidence, then we should consider that in the context of burden. And plus, it's important to work in multidisciplinary teams. When scientific knowledge is so stratified, so segmented, it's important that we have different perspectives from different scientific perspectives, scientific or whatever field that you're working with. I mean, there is this, I mean, if I have time later on, if somebody's interested, I can tell you about this example, which sort of makes this important. Like when you work with a team which is only consists of physicists, they will look at a particular problem as purely as a physical phenomenon, while when you also need a chemical phenomenon, a chemical perspective to that particular problem. And this is an example of that. And local stakeholders should be involved in the process, right? So if it's going to affect people who are going to be the consumers of what you're selling, their perspective also has to be considered in some particular. So having said that, in the last 10, 15 minutes, I'm going to talk a little bit about, okay, as personally from my perspective, what can I do about this, right? I mean, I'm by training, I'm a mathematician. So I'm already working in some sort of abstract space, right? I mean, I do some computation, things like that. But the thing is, how do I engage with something where I can sort of use my knowledge or my perspective to say something meaningful about a real life problem where ethics is important, or a mathematical model where ethical perspective is important. So we looked at this question of how a public transit system is designed. So this is a standard problem for the last 50 years. This urban transit network design problem has been well studied for the last 50 plus years. And there are many different kinds of problems and decisions being made, in different mathematical models which are used and then computed, strategic decisions, tactical, operational. I've given you some examples of this. And this is based on paper with Adam, as I mentioned earlier, on which recently appeared in the ACM conference on equity and access in algorithms, mechanisms, and optimization, which was organized by this really cool. So this is my advertisement number 2. If you are interested in meeting or talking with other people who are interested in using computational power for social good. This is a group called Mechanism Design for Social Good. You can, if you just do a Google search for it, there is a large community of people who sort of discuss things and work with things and organize workshops, discussion groups, things like that related to this issue. So look that up, and you might find, if nothing else, that might be the most useful thing you find from this particular talk. So back to our problem, right? So urban transit network design problem. So it's basically a two-level problem. The upper level corresponds to transit policy design. So when you're making decisions about what should be the costs, what should be the socioeconomic constraints, what kind of constraints should you design the overall region-wide, let's say Chicago Transportation Authority. The lower level corresponds to the users, people who are actually using the transportation system, the passengers, people like me who take the subway or the bus to go to different parts of the city. And the travel choices they make will be influenced by what happens over here. And the choices they make might influence the kind of decisions the upper level makes. Because if you raise the price of buses too much and everybody starts crowding the subways, then you might have to sort of rethink your policy because everybody is trying to save money and getting on the subways and they are getting overcrowded. I'm just making, that's a silly example, but something like that. You understand the point, I hope. And within the lower level, there is another game going on, right? If you think in terms of driving a car or something like that, everybody wants to take the shortest route. But if everybody wants to take the shortest route, does that, it might become so crowded that it's completely jam-packed that nobody can move. And that does happen, right? So there is a game being played between the users at the lower level as well, because the choices they make, they are influenced by choices of other people in that. So conceptually, these two sort of games are tied in together, and together they can be expressed as a sort of a mathematical program, a mathematical description with equilibrium constraints. So it's an example of a mathematical game. So this process is in the standard way is modeled as an optimization problem with underlying game theoretical assumptions. So some of you might know, or if you don't know, that's fine. It's a kind of a non-cooperative Nash game, and there is a Wardrop equilibrium of that. And the most common, so when we have optimization problem, we should ask ourselves, okay, what are we optimizing, right? So the most common objective functions, the objectives we are trying to maximize or minimize we are trying to minimize, let's say, operator costs, right? The number of the travel distance, the vehicle maintenance, things like that, and user costs. You want to minimize the travel time, waiting time, walking distance, number of transfers, things like that. And these are all subject to standard constraints of transportation network design, budgetary bounds and how networks interact, things like that. So we don't have time to sort of talk about the details of that. So the question is, okay, I'm still stuck on this question, right? So how should a public transit system be designed? So I've told you how things are done, right? So it's an optimization problem with the standard objective functions, like you're trying to minimize user cost, minimize operator cost, subject to standard network. And then you can tweak things. In general, these problems are really hard computationally. Right? So these problems that you create this way are really, really highly nonlinear, highly complicated with lots and lots of data that you have to work with. So these are really hard. So a lot of the work is based on, okay, how do I take these models? How do I emphasize a particular objective function or a constraint to alleviate certain particular problem? Maybe there is too much vehicle crowding. So how should I change it so that there is less vehicle crowding and things like that? Right? But let's take one step back and ask ourselves, okay, recently, not that recent, but about 7 or 8 years ago, there was a major review of these problems that were considered. And what they found out was there was exactly one paper where the objective functions or constraints were not just travel time or user demand or operational costs. The standard things, right? You want to minimize travel. You don't care how much pollution you're causing as long as you minimize travel times. Of course, these things are interrelated. So there was only one paper which had considered environmental or health concerns, like in the form of CO2 emissions, out of thousands of papers that have been written. So the question we had was that, how about, okay, here, I want to see how can we design a public transit system to not just to work, okay, to bring people to the downtown, which is good, that's an important part of it. But what about community access to social services? For example, do all communities in Chicago area, all the neighborhood in Chicago have equitable access to healthcare centers, to city offices, to parks, to museums, whatever kind of social service you're talking about? And can we improve this accessibility and make it more equitable? Okay. So how can we do that? So to use as a case model, we worked with the primary healthcare centers in Chicago. So these black dots are, so this is Chicago, hopefully all of you recognize that. And the boundary and the political units, or sort of the borders that I have in the map of Chicago, are the official 77 communities that we have in Chicago. And these black dots are the locations of the primary healthcare centers. Okay. So this is where primary healthcare centers are located. And based on, I'll talk about how I measure this accessibility. Based on this accessibility metric, this is the green colors in the middle over here. The darker the green color, so I don't have a scale over here because that's more complicated to sort of describe what's happening. But these colors in the middle, bright green colors, are the ones which correspond to highly accessible. You can reach your primary healthcare center very quickly and get treated over there. While these neighborhoods, these in the south, in the northwest, southwest, it takes a long time to reach a primary healthcare center from somebody's home on average living there. Okay. So this is the situation, and this is not just situation we came up with or we sort of observed for the first time. This is something which has been talked about by City of Chicago in their official reports as well. So now the question is, how do we improve this section? How should we improve this accessibility? So the traditional way of studying these problems is in terms of facility location problems. So what do? We throw more money at the problem. Like obviously we should be building more primary care centers and then place them optimally, so that more people have access to them. Build more CTA subway lines, build more CTA bus lines, add more CTA buses. But all of these are slow, and they require major financial investments, which might take, for political or economic reasons, that may or may not happen and might take a really, really long time. So what can I do as somebody who might be advising the CTA or a transportation system to do something better about this particular problem? What can I say as an applied mathematician? So what we do is, we consider the problem of changing, rather than changing or adding new facilities, we say, how about we change the transit network? So can we make changes to the transit network in such a way that it improves the problem that we are trying to solve, the equitable accessibility, but without making any changes that are disruptive or expensive, right? So it almost seems like, I want my cake and eat it too, right? So I want both these things. So this is what we build a model, a mathematical model along the lines of what I said. So we took a standard model and we tweaked it. So we build a model in such a way that we want to build a model in such a way that we produce solutions that remain at or near the system's current cost and performance level, while trying to improve the social access objective. And the design decision should consist of measures which are low cost, immediate, and easily implemented. Right? So these two are sort of two of the crucial design principles over here. So I'm not going to bore you with the mathematical description of this thing. So the main point I want to make is that how did we achieve something like this with a reasonable rate of success? So this is sort of, ignore this part. The rest of it is a very standard model for public transit design. Except this and these two functions, whatever they are, operator cost and user cost, they are usually the ones which are the objective function you're trying to optimize. And the decision variables we created are basically, how can we exchange buses between different lines in such a way that it improves accessibility to primary healthcare centers without being disruptive. So I'm going to skip over these mathematical details. If somebody is interested, I can talk more about them later on. So we had to do something. I mean, this is the accessibility metric that we're using. This is a standard thing. I mean, one of the motivations we had, this comes from geographical information systems. So a lot of work, and some of you might even remember from a few years ago, a lot of work was being done to understand food food deserts, places where people don't have quick access to fresh food. So this is a one sort of metric used to understand how quickly, how accessible is a particular collection of locations. For example, grocery stores with fresh groceries. So we use this sort of standard function. It's highly nonlinear. There are certain parameters over here, and you take those, and we use that as a measure of how crowded a particular facility is and whether it's close to many populated communities. So this is sort of the mathematical formulation of this principle over here that I have over here. Yeah. The other thing I want to say is, how do we make sure that we don't just make the problem, while improving the accessibility to primary healthcare centers, we don't disrupt other people's accessibility to, for example, their downtown jobs and things like that, or moving around the city. So what we say is that, oh, let's say this is my current operator cost, or this is my current user cost. I'm allowed to make it worse by a really, really small amount. So in our case, we use like 1%. So up to 1%, I have the flexibility to make it a little bit worse. Okay, so I'm going to skip over this and sort of, this is something that a lot of you might be interested in. I'm just giving you one slide for this. So what actually are we doing computationally? Right? So computationally, we're building an underlying transportation network, which has these many nodes after certain reduction in and the nodes correspond to origin destination, where people start from and end at, public transit stops, communities, and primary healthcare centers. So there are a total of these. There are a total of these many arcs, which correspond to walking routes like this, the CTA bus and subway lines, things like that. Yeah. And then all the data sources from, this was before we started work on this, before 2020 census data became available. So this 2010 census from the CTA GTFS files and healthcare data. So using all this data, and we had to create a new algorithm to be able to work with, because it's a highly nonlinear optimization problem with really large scale data. So it's hard to work with this. So I'm just saying these words for those of you who might have experience with taboo search and simulated annealing. So we created a hybrid taboo search simulated annealing solution with this. And this is what the computational results look like. So this objective function is the value of the accessibility, the objective function value. And as we run the algorithm, it improves that accessibility. There is a bump over here. This bump corresponds to when we allow buses, or when the algorithm starts moving buses from regular routes to express routes. So express routes are the routes which skip over certain, they are faster, and they skip over some less used stops and go to the more used stops. Yeah. So let me, and at the end of these 500, we stopped out of 500 iterations because there were no more improvements showing up. So what happens? So don't worry about the actual numbers. The numbers are not, these numbers are purely used for comparison purposes. So this is the objective function value in terms of the accessibility to something. So this was the initial value, and this is the final value. So the mean hasn't changed much. The median hasn't changed much. The maximum, which is good, right? We want things to be more accessible. The maximum hasn't changed much. But what has changed is the minimum value. So this corresponds to where the accessibility was very low. That has gone up by 45%. Standard deviation has decreased by 33%. So what all this means is that overall distribution remains relatively balanced. Things overall, things moved, but what happened was the maximum value remained the same, but the minimum value went up, and the standard deviation became less. So most cities, there is an equitable distribution of what the accessibility is in most of the communities. Overall, we have success in terms of what we want. And all this was done without making the overall thing much worse, right? We only allowed degradation in the overall thing by a percentage of 1%. That was the parameter we used over there. So this is how it looked initially. And after we run the algorithm, 500 iterations, and move some of the buses from one line to another, this is what the accessibility looks like. And you can see that it became more muted, right? There are fewer greens, but there are also fewer red color things. Everything is more gray, and which is good. Everything is more equitably distributed. This thing is still deep red, and if I have time later on, I'll ask you, for those, I mean, all of you are from Chicago, you might have an idea why this is still red. Okay, and this is a relative change that happened. So you can see this is the transfer of resources, relatively speaking. And I'm going to stop since I am out of time. I'm going to stop and thank you for listening. And I'm going to give you an opportunity to ask questions, and we can go back to certain slides as needed.
Great, thank you. Anyone is free to unmute themselves, or if you're more comfortable, you could also put a question or comment in the chat.
Thanks a lot, Hemanshu, for all the pointers to ethics in addition to the mathematical modeling principles. So I have taken a quick look at your paper, and I'm curious that the objective function values seems to be very small, like at the order of like 10 to the power -4 or even 5. Is that correct?
Yeah, I mean, that's just an artifact. I mean, all of those things, the actual numbers, so these objective functions are based on, let me share the thing again. Let me show you the. Right, so that's just an artifact of using this particular. So when you use this particular gravity-based metric, okay, when you use these gravity-based metrics, they are only useful for comparative things. So the actual value of the objective function is in some sense meaningless. It's just it's used for comparing how things were earlier and how they have changed, whether they have improved or worsened in terms of accessibility. So that's
right. So I mean, your algorithm seems to be very complex, and I don't really understand the details. But I'm guessing that you show a graph like when the objective function reaches a plateau at the 500th iteration, then the algorithm stops. So I'm imagining your stopping condition must involve some change in error or objective value, so that it's
so no, I mean, we stopped it. Yeah, we actually stopped it way before that. We stopped it because it's as you know, it's a very complicated problem, so it takes a long time. So once we saw that there were no further improvements happening, we stopped it like manually in some sense, right? So after a certain point, we just stopped it. Not so it didn't even reach the point where there was a numerical constraint on stopping. So we stopped it before that. And in the paper, you can read about, we did some test studies to see how sensitive or whether it was possible to make any improvements even in some simpler situations based on the data. So we generated some test networks and worked with those. And our conclusion was that it would be not very useful to go beyond. I mean, it's not going to show any major improvements, even if we went on to 1,000 iterations or something.
Oh, so I mean, at the 500 iteration, it reaches the objective value of around 10 to the power -4. But then the computational results where you show the statistics have all the values at the level of 10 to the power -5. And
I mean, so, I hope I didn't make an error in my slides. So I don't know. I mean, let me see. Okay.
Maybe there are different.
Yeah,
I don't know. Maybe
that's not. Yeah, I mean that picture. So let me see.
Yeah,
that's a good question. I mean, that could be just. So yeah, 2.6 and okay, yeah, and right there is. Yeah, you're right. I don't know why there is this discrepancy. I will have to look into that. Yeah, I mean, I'm not sure. I don't have a good answer for you. This 10 to these numbers don't seem to match up with what I No. Okay, no. I know what's happening. Sorry, yeah, it makes sense. So it's off by a factor of 10, right?
Right.
The reason it's off by a factor of 10 is because this is for the community areas. There are a total of around 77 community areas. So you should think of this as when you multiply it, or when you add up these numbers for 77 things, it will give you something like 10 to the power minus 4.
Okay.
These are the mean, median, standard deviation for, or so you have a vector of data, right? 77 for each of the community areas, because we are trying to understand what the accessibility is for each community area.
So the previous graph is maybe for just one of these 77.
No, not one. It's for the sum of those things.
Oh, sum of those.
It's the sum of those things.
All
so
right.
the objective function is,
Okay.
So this is the objective function. So it's for the sum of these things. I didn't really talk about this. It's actually a little more complicated than just a simple sum, but it is basically adding them up. That's right. So that's why that's the difference.
Okay. And I imagine like during different hours, like peak hours or off-peak hours, the data and all these accessibility concern or just the regular user calls could be very different. And
they would be, of course. Yeah, of course. I mean, we mostly worked with daytime or a particular time period in the daytime because that's what makes most sense for primary care healthcare center. I mean, nobody will travel to a primary healthcare center late at night or early in the morning. It's only during the regular hours. And we do make an assumption to make this computationally work, because this is more of a design tool or a decision-making tool. It's not really a tool for a live updates, right? So this algorithm or this model is meant for upper level design decisions that you're trying to make. It's trying to help you come up with possibilities of making changes to the transit system so that it shows that kind of improvement. So you would not run it on dynamic data. You would actually run it on static data, but you can take that dynamic data and look at different time intervals to make sense of what's really going on. And we picked basically one particular time interval and sort of averaged over that time period.
Right. Yeah. So very interesting. Have you maybe presented this work to maybe some officials at the city of Chicago, or heard any feedback from
I mean, so we have,
decision makers?
Yeah, exactly. So some people in the administration in IIT have been trying to get in touch with people in CTA, but it's hard to get people who are at the higher level at CTA to really talk to them. So it's I'm still hopeful that maybe something will come out of that, and I'll be able to talk to them about this. So as a decision making tool, basically.
Okay, very interesting. I don't want to monopolize the Q&A time.
No, I mean, yeah, anybody
from the other participants.
And for those of you who are, I know this group is more focused on maybe computational issues. So if you are interested, I mean, if you're interested, you can send me an email, or if you just do a search for this particular paper, the paper that the second part of the talk was based on arXiv as well as on Adam's webpage, we do have all the data that we used, all the algorithms, all the software, everything that, I mean, Adam did most of the work with the actual computational work, writing the C++ code. He used C++ for it to actually make it work. Otherwise, it was too efficient to do it with something else. When he tried Python first, and that didn't work so well for him, so he ended up doing it with C and C++.
Oh, so how long did it take to maybe get to a solution estimate for?
I mean, it took, so I'm trying to recall, I think it took a few days, but he just ran it on his personal computer. We didn't actually try to use a cluster or something like that. I think on a cluster, it would be definitely, would be faster. And the key point is we were not really trying to optimize this in some sense, the running time, because as I said, it's an offline decision-making tool. So once you run it once, it sort of gives you these different possibilities of how to move buses between lines so that you have an improvement in accessibility. So it's not something that you would actually run every day or or very often in some sense.
Yeah. Well, we have run over time, so I'm sorry. I better pass it back to Rebecca.
Sure. Thank you, everyone. Thank you especially, Dr. Kaul. This has been a really unique talk. We don't often have talks like this, so I really appreciate it as well. Okay, nice to see everyone. We'll see you in the new year.
Thank you so much. Thank you, everyone.
Thank you.